Okay, let's have a look at your last assessment. So question 1, battery consists of 4 cells, each one with 1.2 volts in series. Okay, very important. Calculate the EMF of the battery. Since they're in series, it's simply you add them up. 4 times 1.2 equals 4.8 volts. Easy, 1 mark. Second one, we have a circuit with 4 resistors, each one with 12 ohms. Calculate the total resistance. The thing that I advised you to do, and it's very helpful in my opinion, is to always label in the diagram the values that you are given from the exercise. So the resistances, for instance, and which currents are passing through which branches. So in this case, not only have I labeled the values as 12 ohms, but also I've given names like R1, 2, 3, and 4, which will help me to calculate the total resistance. So what I can see easily is that the 2 and 3, with my labeling, they are connected in series. So the combined R2 and 3 is going to be simply adding them together. So that gives me 24 ohms. Now I also see that the 2 and 3, the effective of them is connected in parallel with R1. So the R1, 2, 3, following the formula, is going to give me a resistance of 8 ohms. And now I know that those 3 combined, they are connected in series with the R4, and therefore the combined R1, 2, 3, 4 simply adds up the 8 plus 12, which gives me 20 ohms. Okay, so wasn't easy, wasn't too tricky. I think it really helps if you label everything on the diagram, and then you can really see how everything works. Next question, you want to calculate the reading on the voltmeter, which is basically the voltage across R4, which is the current times the R4. Do I know the current? No, I have to find the current. How can I find the current? It's the same current that goes through the whole circuit, okay? And this one, I'm taking advantage of the fact that I do know the EMF of the circuit, and I do know also the total resistance, which I just calculated in the previous example. And usually this gives you an indication that probably you have to use what you just calculated in the previous problem. So EMF over the total resistance is going to give you the current, which you're going to plug into this equation, and this is going to give you roughly 2.9 volts. Next question, you have this diagram and they ask you state the name of component A. Easily, that's a diode, okay, very carefully. It's A, we're not looking at B, which is a lamp, or C, which is a resistor. So I told you that the symbols of the electrical components, they are quite important. Next question, another gift for 3 marks this time. Calculate the combined resistance of 2 resistors when they are in parallel. You use the formula and you get 1.2. If you use the other formula, the 1 over R total equals 1 over R1 plus 1 over R2, do not forget to flip the fraction at the end. And some of you did forget, okay? So choose very wisely which method you're going for. Another circuit, 12-volt battery, 2 identical lamps, and the fact that they are identical tells me that they have the same resistance, okay? So I also know that the same amount of current is going to pass through them. So all of this information I'm already putting in my head or even writing down before I even get to the question, because this might actually help me. When the switch is closed, the ammeter is reading 2.4 amps. So again, I've labeled everything. Calculate the total resistance. The total resistance is going to be calculated from the formula that gives me the total current, and I'm using the EMF. So the EMF is the 12 volts, the current is 2.4, so I'm getting 4 ohms as the combined resistance of the full circuit, which is composed of 2 identical lamps with the same resistance and 1 resistance Q. Now each lamp has 3 ohms resistance, which I also labeled. Calculate the resistance of Q. I know the total resistance. Right? So I know R1 and R2 are connected in parallel. So I can get the effective resistance from those 2 of them with the formula, so it's 1.5, and I know that the total is going to be equal to R1, 2 plus RQ, so simply subtract them and I'm getting 3.5 ohms for the resistance of Q. Next one, very similar, actually the same circuit. This time they give you, they ask you to calculate the power supplied to one lamp, which already I know it's V times I, but which V and which I. So in this case, I've labeled the edges of the lamp as A and B. So it's VAB, so the PD across one lamp, AB, times the one current, I1. But I also know that the currents, because they are two identical lamps, as I have here, it's going to be equal to each other. And since the total current that's coming here, the I, is equal to 2.4 and then it's divided in 2, then the I1 is going to be 1.2 amps. How do I get the potential difference across AB? Again, this is going to be found by applying Ohm's law in this part of the circuit. So the I1 that's entering this junction here, this branch here, is going to be VAB over the resistance of the lamp. I know the resistance of the lamp, I know the current, and then I can calculate the PD, which is 3.6. I substitute that in this equation and I'm getting the power, okay? So one calculation is allowing you to move on to the next one, okay? So it's like a domino effect. You can't simply sometimes substitute numbers and get the value. Some questions are easy, but others require intermediate calculations for you to get to where you want to, okay? Always think in terms of what am I missing from this formula and how can I get it from the rest of the input from the exercise. The next one, with the buzzer, the thermistor, the temperature increases. What's happening, state and explain, okay? Very carefully, when the temperature goes up in a thermistor, we know that its resistance will go down, okay? And if the resistance goes down, then simply the current will go up. That's it, okay? 2 points. So just the possible use for this circuit. Again, different answers here. To be safe, since it's a buzzer, which means something that will make a noise, always go for something that would alarm you, okay? So like a temperature sensitive device that would give you an alarm, so like a fire alarm or a warning, okay? That's what they were looking for. All the refrigerators and ovens that you wrote, they were kind of correct, but because of the buzzer, like as I told you, I haven't seen any refrigerators or ovens with the buzzer when the temperature goes too high. Maybe, okay? It's 1 mark, just play safe. Define EMF for 1 mark, again theory. Energy supplied by a source in moving a charge through a circuit per unit charge. We have more definitions in our slides or in your textbook. Use those. Do not, please use the definition from the syllabus, okay? It's missing 1 part. Next one, another circuit, very simple. They give you the resistance, they give you the voltage, they want you to calculate the reading of the ammeter, V over R, 3 over 4.75 amps. So be very careful with what you put on the numerator and what you put on the denominator, okay? One component is reversed in this case, which is the diode. State the reading on the voltmeter and explain your answer. Since the diode is reversed, we know that in the reverse mode it has very, very high resistance, which means it will not allow any current to pass through, and if this is happening, then the reading will be simply 0. The next one, which troubled all of us, a lot of information here, okay, but very few points that we actually need to solve it. First of all, it asks for the rate of energy transfer. Rate of energy transfer, we need to identify it as E over T, so energy over time, which is for us power. And power is V times I. Just by doing that, you get 1 mark. Just by doing that, you're getting 1 mark. So make sure, even if you don't know which voltage and which current to use, please do that. The formula always gives you some marks. Now, the current was something that most of us did correct, okay? So all of us used the 3.5 amps. The problem was with the voltage, so which voltage to use. So it's asking for the rate of each cell, okay? And if I look at the example, I have 990 cells, each with an electromotive force of 1.2. So each cell has 1.2. So this is the voltage I need to use. The ones who you use the 54, look at that. The cells are contained in packs in which all the cells are in series with each other. The EMF of each pack is 54. So you use the EMF of each pack. So you could have calculated, in this case, the rate of energy transfer on its pack, but the question is about its cell. So those values, the V and I, need to refer to its cell. So read this question very, very carefully. As I told you, they can give you a lot of information, useless information, just to throw you off, or in this case, this question in the exams could have had more questions that we didn't include in this topic because they were not relevant to Unit 4, okay? Describe what is meant by electric field, also theory that we need to know, a region in which an electric charge experiences a force, direction of a force on a positive charge, that's all theory. Next one, calculate how many electrons pass through the copper in these cases. So you want a charge, okay? So simply doing I is equal Q over T, Q is I times T, 3 times 60, that's 180 coulombs, okay? And then you know that one electron has a charge of 1.6 times 10 to the minus 19 coulombs, and you have now 180 coulombs, and you're asking how many electrons is that? Okay, so it's a simple math question. So it's just the ratio of the two. So it's 1.1 times 10 to the 21 electrons. The next one was, I told you about resistivity. It's this type of question that appears in the exams. The fact that they're same material means that you have the same resistivities, which you can equate them. So this is the formula, nothing special. I've circled the only unknown, and then I have solved my equation for this unknown very, very carefully. So check your math that you are able to go from this step to this step, okay? And then I substituted, only then I substituted the numbers. The reason why I haven't done any unit conversions is because they're fractions, so I know that they will be cancelling each other out. If you did, that's fine, it's just that it took you a bit more time. The next one, calculate the current when you know the voltage and the power. Simple formula, 2 marks, you say thank you and you move on. Suggest a suitable fuse for this system. Anything above 39 amps, like 40, 41, 42, 43 would be acceptable. Just give a number, okay? The next one was also a bit tricky. They ask you to basically give a graph of how the resistance of this wire is changing with the length, which is basically the experiment that some of you did in class after school. So we know that the resistance is increasing with increasing length, and we know the value that we have is just that when we're at 1 meter, the resistance is 7.6 ohms. So we have to include those values in our graph, okay? So the last point is the 1 for length and 7.6 for resistance. That's one data point. It's a straight line passing through the origin, always with a ruler, please, okay? The units are already there, so you don't have to worry about that and the labels. That's absolutely fine. Now you have the 12 volts EMF on this circuit with 1 meter length. Calculate the current, V over R, 12 divided by 7.6, easy, 1.6 amps. The next one, which troubled us a bit, calculate the PD when we are at 0.35 meters. So basically you are shortening the length of the wire, okay? So instead of taking the full EMF, which is the 12 volts, now you're taking, let's say, 35% of that, because with 1 meter, you're taking 100% of that, like 12 volts. So with 0.35, you're taking 0.35 times 12, which is 4.2 volts. And the rest stays in the circuit, okay? And it goes to the rest of the part of the circuit. So there is voltage dropped as well there. Calculate the charge that's passing through the resistance in 5.5 minutes. The first thing I'm doing, converting the 5.5 minutes in seconds. So even without the calculator, I break it down as 5 times 60 plus 0.5 times 60. That's 330 seconds. Formula for current, I times T, 1.6 times 330, 528. Again, many formulas that could give you a mark or two. So always write down the formula, even if you don't know how to properly use it, okay? This would secure you some points. The diagram shows a sphere that is negatively charged. Draw arrows to indicate a pattern and direction. So it's a negative sphere, which means the arrows need to be pointing inwards, okay? My arrows are terrible, so please do them a bit better. I'm not an iPad expert, so the arrows, they have to be pointing inwards because I repeat, it's a negative sphere, negative charge, and you have to make those lines always pointing to the center of the circle to get your 2 marks. So straight lines and also the direction matters in this case. The next one we avoid. Now we have the 2 conducting plates connected to a battery. We need 5 at least lines to show the electric field patterns. Be careful, plus and minus, okay? So you can't just simply decide which one is plus and which one is minus. So the left one becomes positively charged, the other one becomes negatively charged, okay? So we're having our field going from basically left to right, positive to negative, and we need 5 parallel lines, ideally equally distant, okay, because it's a uniform field, ideally, as I said, and you don't need to include the lines on the sides, okay? This is not necessary. Just 5 parallel lines and with the direction from positive to negative, it's absolutely fine. Next one, we have the current in milliamps, which means we need to convert in amps, 10 to the power of minus 3 amps, very, very carefully, and 10 hours, that's in seconds, 10 times 3,600. I told you in physics, you will very often have to convert hours into seconds, so you can already put in your mind that 1 hour has 3,600 seconds because it's 60 times 60 times 60. So, and you can directly do that calculation. Same formula again for charge, which is current times time. It gives you the charge in coulombs. And the energy in the battery, it's V times I times T. The V that I told you, the V is 1.2, and the I times T is basically what you calculated before, so you get the 9,000 something joules. Difference between conductors and insulators as a simple electron model. We have the free or delocalized electrons in conductors that allow those electrons to move freely and basically carry electricity with them, which is the flow of electrons. And in insulators, we don't have those free or delocalized electrons, so there's no electrons flowing or moving freely, which means current cannot flow. Here we're looking at an electromagnet. 1 mark and 2 advantages. We can switch it on and off whenever we want by switching on and off the circuit, and we can control its strength as well. Next one, state and explain what you can deduce about the metal bar. So the metal bar is a magnet. That's what we can deduce, a permanent magnet. And how did we get that? Because we see that the X is repelled by the north-south, by the North Pole, and also the X is attracted by the southern one. So there's only one plausible explanation here, that X should be the southern pole, okay? And that's how we get 2 marks. And the last one was about changing the strength of an electromagnet safely. Just simply increase the number of turns in the coil or increase the current passing through, not the voltage or the PD, even though I did accept it for some of you, okay? Go safe and go with the current increase. Be very careful with your calculations. You see how often you use those formulas in this unit, okay? Do not come in the next test without knowing those formulas and how to manipulate them. And one lesson to be learned for all of your physics journey, but particularly for this unit, even if you're not sure, just throw the formula that you think is relevant, and this, if the formula is correct, this could give you some marks, okay? So good luck with your next one after Christmas.